So today we had to do some questions on op-amps. Okay, some previous year questions. So one of these question is the latest one in ECE. Okay, so the network is kind of slow here. So let me know if you are unable to follow somewhere. Okay. So in this question, two voltage sources are given in the input, right? So you can see the V in is there and Vref is there. Okay, so if V out is 1 volts for V in 0.1 volt. So what they have given is that the value of V out they have given for a particular value of V in, right? So V out is 1 volt for V in 0.1 volt and V out is 6 volts for V in 1 volt. The value of Vref is not given, but it is said it is fixed, okay? And V out is measured across RL. So find out the value of RF by RN. So this is a question where you can see that two sources are given and there are conditions given. So this can be a lengthy question. So if you want to solve it easily, using superposition theorem will be best to solve this problem, okay? So for case 1, when Vin is active and Vref is 0. So I have already solved the problem because I am facing network issues. So when I try to write it, you are unable to see it in live. So let us do it in this way today. So Vin is active and Vref is 0. Okay. So one of the source we are taking as active, another as dormant, because this is how we solve superposition theorem, right? If there are different sources in the circuit, we take one of the source, solve the circuit, take another source, solve the circuit, and then we add it up. That is what superposition theorem is. Okay. So now you take V in, and when you take V in, Vref will be 0. Okay, so that's why this node is grounded here. This one is grounded. Okay, and then you see now that it's a simple circuit where V out 1 is minus RF by RN into V in. You can directly write. Right, you need not solve any KVL equation for this. This is a simple circuit because this is 0 volts. Right, you know that this is 0 volts. Right, so this circuit is as good as this circuit. It is just this circuit right now, right? So now you see that in the problem it was kind of looking very complicated. If you want to apply a KVL directly here or KCL, you will assume a voltage V here and that the same voltage V will be here with virtual ground concept, and then you have to solve the KCL equations, right? But when you tried using superposition theorem, you are now grounding one of the source and you saw that it is so easy that you can directly write the equation. So this is how you save time in competitive exams, right? So this speed will come, which theorem to use, that idea will come only from practice. Okay. Okay. So now let's start again. So V out 1 we have found, which is only purely due to Vn, right? Now case 2 is when Vn is 0 and Vref is active. Now you see that when Vref is active, Vn is 0, I have grounded it, this node I have grounded, and VRF is active, right? So this is now a non-inverting amplifier, right? And now you can, if you want, you can just put a KVL equation in here, okay? And that you can write, and you will arrive into this formula. So I'm not solving it. If you want, I'll wait. You can solve and see. You will get this value only. Okay. Vref minus R2 upon R1 plus R2. Okay, so now V out will be V out 1 plus V out 2, and therefore you arrive at this equation. Okay, here, right? Now you have the condition. You have two conditions. V in is 0.1 volt, V out is 1 volt, and another condition where V in is 10 volt and V out is 6 volt. Now you directly need to put it, right? So when V in is 0.1 volt and V out is 1 volt, if you put it, you will be getting this value, right? This value which I have marked in red, you will directly get as 1 plus RF by Rn into 0.1, right? This you can put in the next equation, which will come from the next condition given. Okay, so I hope you are able to follow and I am not very fast. So when you now try to solve both the equations, you will arrive at the value of Rf by Rn, which is asked in the question. So the problem was very simple here, but the catch is how to solve it, right? So now if you in the equation 1, now if you try to open the brackets and do some things like take Rf by Rn common and then do things, it will be complicated. So better leave it like this, and we will directly substitute it in the next step. You see, so this is first condition born out from this which is given in the question. The second equation is born out from this which is given in the question. In the second equation, I am directly putting from 1 this entire value of 1 plus Rf by Rn into Vref minus R2 by Rn1 plus R2. I have directly put it, you can see, right? This value here, directly put it. And therefore, easily you can solve. So, if you open the brackets in the equations, try to club in Rf by Rn and then put, you will get the answer, but that will eat up your time. So, you have to do smart work here, okay? So, remember these points. Okay, so this will be beneficial, and these kind of questions you should practice, and you should use these tricks while practicing, so that in exams it is easier for you and less time consuming. Now you see how many steps I have done. I have not done many steps, right? And the solution is there. So first I did the superposition theorem, I got the conditions, and then I simply took out the values and I put it in there, plugged in the values, and I simply got the answer. Okay, so is this question clear? It's a very simple question. There was nothing in it but high chances of getting silly mistakes while calculations, and you can use some tricks and tips to uh, make the solutions short. Okay, so if this question is done, then I will move forward to the next question. Let me know. Should I move forward? What about Chandrasekhar and Swati? Have you followed the question? Okay. So today we will be doing only Opamps. I have selected some questions from Opamps. So this question was GATE 2014 set 1. It's a simple question. Okay, there is nothing in this question at all. You only have to put KVL, KCL, or if you know how the behavior of an low pass filter circuit, you can directly would have solved the question. Okay, so I'm going to solve the KVL or KCL equations. Okay, so you see from voltage ground virtual ground concept, this is a 0 volts node, right? And you only have to apply KCL, right? So now I will again put a trick. I'll show you a trick here. So this is R and this is R2, this is C, right? So now when you're putting a KCL equation across this kind of circuit, what you can do is, if this is 0 volts, this is V in, right? So what we do in KCL, this is one current, this is one current, and this is one current, right? So what you do is 0 minus V in by R plus 0 minus V naught upon 1 by SC, because this is C, plus 0 minus V naught by R2 is 0, right? Now instead of this, there is another thing that you can do. What you can do is you can write the admittance instead of impedance. Okay, so what you will do, 0 minus V in by R plus, you see admittance add up in a parallel circuit, right? So admittance add up in parallel circuit, right? So what you will do, 0 minus V naught common, and what is the admittance of R2? It is 1 by R2. What is the admittance of C? It is SC. 1 by SC is the impedance. You can directly write it in multiplication form, because admittance will multiply to the voltage. Impedance gets divided, V in by R, but admittance will get multiplied, and that equals to 0. So I'll just wait for some time because of the Wi-Fi, it is not getting updated. Okay. So let it get updated. Till then I will just solve it. So please solve the equation 0 minus V in by R plus 0 minus V naught bracket 1 by R2 plus SC equals to 0. So if you solve that equation, yeah, so now it is updated. You can see that 0 minus V in by R plus 0 minus V naught into 1 by R2 plus SC. Any doubt in this equation that I have written? You can ask right now. Any doubts here? Okay, so there are no doubts. Okay, that's good. So V naught upon Vn is therefore can be written as R2 by R 1 by 1 plus SCR2. Now you can see from this term SCR2. So I am going to expand and write it R2 by R 1 by 1 plus J omega upon 1 by R2C. Right? And therefore the 3 dB bandwidth here. Okay. So the cutoff frequency it is given. So the cutoff frequency here will come out to be omega cutoff will be what? 1 by R2C. And omega cutoff is given as 5 kilohertz. So 2 pi into 5 into 10 to the power 3 is equals to 1 by R2 into. So it will get updated. Yeah, my Wi-Fi is actually very slow. So that's why it is updating late. Okay. Into C. So the value of C is 10 nanofarad. 10 into 10 to the power 9. And please find out and tell me what you are getting as R2. Okay, so this was a pretty easy question. If you know the concept of low pass filter, you would know that the omega will be dependent on R2 and C only, and from there you would have directly written and got it, or otherwise you can solve it. It's a two-line solution. Okay, and from here you will get the value of R2. Please let me know what R2 are you getting. Okay. So as I always say that before starting analog electronics or any other subject, you should be very much proficient in networks and signals. Okay. So in every step while solving the questions, you could see that network and signals are inevitably used. And we will see another question which is related to transient analysis. I'll take that up in last. And you'll see that it's completely, you should know the transient analysis from network systems, so to solve those kind of questions. So let me know what value of R2 you are getting. Okay, so I have one answer. Chandrasekhar, what about you? Have you solved? So 3183 ohms is the correct answer. It is 3.183 kilo ohms. Okay. So in the question, I think they had asked it in kilo ohms. I think, yeah, the value of R2 in kilo ohms. Okay. So 3.183. So this thing also you will have to remember that in numerical answer type, be very careful about the units. Okay. So you should see the unit and then you put in the answer. Okay. So right now I had not shown you the question for long, so that is fine. But always remember in numerical answer type questions, whatever you are asked for, look into the unit and then answer it. Otherwise, it will be wrong. Even if you have solved it correct, it doesn't matter. The answer is wrong, right? Okay. So then, okay. So I'll move forward with this. This is a GATE 2013 question. It's a very simple question. It was a 1 mark question asked. Okay, there is nothing tricky in this question. Okay, uh, the only thing that can go wrong is that you need to find the region of operation and those kind of things. But this question is nothing but op-amp as a logarithmic amplifier. Okay, and it will be biased the way it is always biased. And there, I don't think in this kind of questions, when they are asked for 1 mark question, there is nothing tricky in it. You normally have to just solve it and get the answer. So you see that output voltage is asked, nothing is given. 5 volts is given here, so the 5 volts is given, this is 0 volts, so that means a 5 milliampere current will be flowing, and this current here is 5 milliampere, right? And the voltage here will be plus minus 0.7, right? So I'll wait for some time, let it get updated, whatever I have written. Yeah, so the voltage VB to E will be 0.7, right? So you just put a KVL here, then a KVL from this loop to V out. So what you will get? Plus 0.7 plus V out is 0. So 0.7 plus V out is 0, and therefore V out is minus 0.7. So this was a logarithmic amplifier, op-amp as a logarithmic amplifier. You should go and check this out. Okay, op-amp application as summer as a difference amplifier, logarithmic amplifier, and an anti-log amplifier, also as a multiplier. So these are actually favorite topics for professors also when they take your interviews in IITs. Okay, and you see in the circuit, in place of the transistor BJT, you can also, they could have also used a diode, and the cut-in voltage across diode will now give you the V out. Okay, so in place of BJT, a diode can also be used, and that is also a log amplifier. Okay, log or anti-log, anything. So this is a logarithmic amplifier. Okay. Okay. So I hope this question is also clear. You can check out these topics later when you go back. Okay. So we have till now done 3 questions. Some of people have joined now, so I'll just repeat that we have done 3 very simple questions. Okay, and yeah, let me just go on to the next set now. Yes, so again, so this is a complicated looking question, but it is rather very simple, I would say. Okay, so what was asked in the question is that they have given one signal. Okay, they have given this signal which is Vi input, this Vi here. Okay, and they're asking that how many times this LED will glow. So what they have done basically is they have used a BJT, used an op-amp to control the base of the BJT, right? You can see the base of the BJT here. So let me redraw this because it's not very clearly visible. So let me redraw it here. Okay, so VLED they have given as 1.5 volt, VB they have given as 0.7 volt, VCC is already given plus 10 volts, minus 10 volts, and beta they have given as 100. So what is this circuit actually doing? Okay, let's see. So we can directly solve this question. It's easy, but I wanted you to understand what the circuit is doing. So they have actually used an op-amp to make a decision whether the LED should be on or off. Okay, you see the op-amp is not connected in any kind of feedback. That means it is making a decision between inverting terminal and non-inverting terminal, right? So this voltage here, okay, this let us say Vx. So Vx and Vi will be compared, and according to that the output here, I am denoting it as Vb. The output Vb is going to be changed. Now if the output Vb is not sufficient enough to give plus 0.7 volts to the BJT, then the BJT will be off. And if the BJT is off, that is if this is not in forward bias condition, the input is BE, base to emitter junction, is not in forward bias condition, that means automatically your LED is not going to glow because there is no current flow, right? And if your VB is high enough, it is high enough to provide current to the base of BJT such that the base to emitter is biased with 0.7 volts, there will be a current flowing, and therefore there is a chance that the LED is glowing. Is this clear? So if there is doubt here, you can ask right now, whatever I am saying. So the purpose of the circuit is clear, right? We are basically using an op-amp to make a decision to put a voltage to the base of BJT so that BJT gets biased, and therefore there is a current flow in the output of the BJT, which will ultimately lead to LED glowing. Now in the question they have given a graph, okay, and they are asking that if this is the input Vi, then please let us know how many times LED will be on. Okay, so your first task will be, what is the voltage Vx, right? So what is Vx? It is simple voltage division rule, right? So what is Vx? Vx is nothing but 2 by 2 plus 8 into 10, which is 2 volts, right? So Vx is 2 volts. So Vi now gets compared to what? Compared to 2 volts. So now directly in the graph you see that this is my 2 volts line, right? So whenever the voltage, input voltage is above 2 volts, my LED is going to glow, right? Why? Because this is a comparator circuit. The op-amp is behaving as a comparator now. So whenever Vi is greater than Vx, since Vi is at positive terminal, Vb will be equal to what? Plus Vcc, right? It will be directly equal to plus Vcc. Either it is plus Vcc or it is minus Vcc, right? So Vb is plus Vcc, and plus Vcc is nothing but 10 volts. And 10 volts is good enough to bias a 0.7 volts, right? Because there is a 15K here. So the IB will be 10 minus 0.7 by 15. And that is a good IB. That means my input is forward biased. B junction is forward biased. And therefore, since B junction is forward biased, the IC will flow and the LED will glow, right? It will be sufficient to put the LED as 1.5 volt. If you want, you can try to find out the value of VCE and everything and see if the active region is following or whatever is happening, and you will see that you will be getting the answer properly. Okay. So yeah, so basically you normally see that there is a V out here. In place of V out, they have just put a LED, and the LED is now working as a load here, right? But the LED is put between these two terminals and not between this V out and ground. Okay. Okay. So okay. So now that means that whenever the waveform is above 2 volts, I should get the LED glowing. So now you see the waveform is going from this value here it is going, right? So first time the LED will glow, it will keep on glowing. Now it goes down, so LED will be off, LED goes off, Again, when it goes up, LED will glow second time, but now it is not coming down, and this is important, right? And it is going like this. That means the LED will keep on glowing. This is important. So here the question, if you do not see the waveform properly, you will make a mistake. Now again it went down, it was off, and again with it up, third time it glowed, and this is the number of times the LED glows, 3. 3 is the answer. So here the confusion could have been 3 or 4, but if you look into the waveform properly, the answer is 3. Okay, so now you can note down this solution. Okay. Let me know when you have finished. Okay. So these kind of questions are expected from op-amps. Simple questions from op-amps can be asked for 1 marks. A bit difficult questions where they combine op-amp with a BJT, and there are this kind of uh, a bit of a different kind of an operation involved. These kind of questions are also expected. Okay. Okay, so one is done. What about others? So whenever you see these kind of questions, don't get afraid. Don't think that, okay, this is something very different and I will just leave that question or something like that, because you know there are so many things there. There is this op-amp, LED, BJT, and the waveform is so complicated looking. First time you just see the question and you think what have they given, and so that fear should not be there. Okay, that will mess up your exam. Just go through the question properly, try to understand it, solve it. Okay. Okay, so we saw first question which had where we applied superposition theorem. One question we saw. Okay, so just show it to others. So there was this one question where there were two sources and we applied superposition to solve it. The next question, this was a frequency response kind of, a low pass filter was given and R2 is asked, frequency is given, so this was an easy question. Okay, the next question we saw, which was a logarithmic amplifier, that is also an easy question. This was a 1 mark question in grade 2013. And this is the next question that we saw. Okay, so yeah, now let us come. So should I solve another question first? Because I wanted to solve simple problems first actually. So let me solve this one. This is a simpler problem. Okay. So again, you see for the op-amp circuit, they are asking the upper and lower threshold of voltages, right? So what is the voltage V here? So let me redraw it. So this is related to the topic of Schmidt trigger, which is a very important topic. Okay, and you see here that this voltage V gets compared to Vin, and therefore now you actually have a upper threshold voltage and a lower threshold voltage. Okay, so what it will be? So we can write an equation for V, right? What will be the equation for V? It will be V minus 3 by 5 plus V minus V out by 10. equals to 0. Can you tell me what is the value of V you are getting in terms of V out? So value of V in terms of V out that you will get is V out plus 6 by 3. Okay, so I have already done this. So this is the equation, and V is equals to V out plus 6 by 3. Okay, so now what is they have asked is, tell us what is the upper and lower threshold voltages, right? So upper and lower threshold voltages. So that means V in is going to be compared with V. So either V in is greater than V or V in is less than V, and that will give you either it is a V upper threshold or V lower threshold, right? And how we find out is, your output saturation is given as plus minus 15 volts, right? Which is obviously what the output is going to be, plus minus 15. Okay, and therefore what you do is you simply equate it. So V is V out plus 6 by 3. Okay, and V in is greater than or equal to, so let me just put the equal sign. It is greater than, it is actually compared to this, right? So V out plus 6 by 3, let us say V in is greater than V out plus 6 by 3, and this will be nothing but 15 plus 6 by 3, right? And V in greater than this value, which is nothing but 21 by 3, 7 volts, right? So V in is greater than 7 volts, that means V out is plus 15, which I have written, right? This is what I have written. So I hope you are understanding what I am trying to do here, that this circuit that we are having is going to make a decision, right? The circuit that we are having is going to make a decision, and V out, it is given saturation value, either it will be plus 15 or minus 15 depending on whether V in is greater than V or less than V. So first I find V in terms of V out, because this is a voltage divider circuit that they have given, right? So I found out V, and now I will be putting V out as plus 15. That will happen when V in is greater than some value. That some value is what we have to find in the question. Okay, that some value is called upper threshold or lower threshold. Okay, so UTP or LTP. So therefore this value is VUTP, 7 volts. Okay, and when V out is minus 15 volts, then what is V in? You see, it is 15 minus, so I should have used this directly, I can use, so UTP equals to VUTP equals to, okay, so VLTP is equals to 15 minus 15 plus 6 by 3 is nothing but minus 9 by 3 minus 3 volts. So VLTP is minus 3 volts. So this is the answer. So VUTP and LTP were asked. Okay, in this question I have not mentioned the options. So it was an option based question, not a numerical answer type, and this is how it came to be. Okay, so you should go through this concept of Schmidt trigger. Okay, it's a very good, it's a very important concept, especially for EC people. Schmidt trigger questions. They used to ask a lot of Schmidt trigger question between, I think prior to GATE 2011 they used to ask a lot of Schmidt trigger questions, and now I'm seeing it in GATE 2016. So that means it can again come in the exams. Okay, in future exams it can again come. So let me know if you are done with this, so that we'll go forward. So next we will take one transient analysis. Let me know when you are done. So solving the question is important, but calculations, mathematics, anybody can do. understanding the concept is very important, because next time the same question will not come, but the kind of question can be similar. A similar question can come with a bit of different concept, right? So if you understand this concept very well, you will be able to solve that one also. Okay, so next again we had this diode question. Let me take this first and then last, then two more questions we can do in 15 minutes. Okay, so now in this question you see there are two diodes they have given, right? And in this kind of question what you should do is you should not assume whether the what will happen when the diodes are off or on or whatever, and then start the question. So just think it in your mind, okay, that if this diode D2 is on, what is going to happen? Okay, whether D2 and D1 can be on together, whether D1 and D2 can be off together, whether D1 can, what will happen when D1 is off, what will happen when D2 is off. So I'm beginning the question with D2 off and D1 on. So in the question what they had done was they had given this circuit and they had asked, they have given this various relationships. Okay, they have given these various graphs between V in and V naught, and they have asked which one is correct. Okay, so the first thing that you see is that this is 0 volts, right? This is 0 volts. Okay, so whatever is Vi, depending on that, the D2 will either get on or off or whatever, right? So when will D2 get on? This one is 0 volts. D2 will only get on if this is negative, this voltage here, right? And if this voltage here is negative, D1 is off. That means both of them cannot be on at the same time, right? So if both of them cannot be on at the same time, I have to figure out one is off, one is on, right? Now if D1 is off, D1 I'm talking about this one, if D1 is off, the question ends there itself, because now V0 is 0 because there is no current coming out from the op-amp. Therefore, I'll start from solving D2 off and D1 on. Is this approach fine? Clear to all? Why I started with D2 off and D1 on? So that you have to think. Okay, and when I say think, I mean that you can write it down also. That is fine. But you have to understand that D2 will be on because one side is given as 0 volts. P junction is at 0 volts. That means N have to be negative. It has to be lesser than 0 volts. Then only D2 can be on. Otherwise, I cannot make D2 on. And if this is lesser than 0 volts, if that goes negative, it is connected to P of D1. Therefore, D1 is off. So therefore, I now start with the other approach where D2 is off, D1 is on, and that makes my circuit pretty simple. This is the circuit now. Right? Now it is pretty simple. Just put KCL. Okay. So now I have put KCL equation, KCL here, and this is my equation. Okay, just check the equation. This voltage is 0 volts. So I have just assumed V and I have written the equation, and V is 0 volts. I'll put 0 later on. You can directly do it. So just for the sake of writing the equation, I have written it like that. So I have just put equation here, and if you solve it, you get this. V0 plus Vi is equals to 9 volt by 4, 9V by 4 minus 5, where V is 0, and therefore V0 comes out to be minus Vi plus 5. Okay. So now when Vi is 0 volts, V0 will be minus 5 volts. Great. When Vi is minus 5 volts, V0 will be 0 volts. Great. And when Vi is all positive voltages, what will be V0? So now you have directly V0 equals to minus Vi minus 5. Right? And you can directly draw this waveform. Just let me know if this waveform is something you are able to understand. It is having a negative slope. The slope should be -1, right? And therefore, and if you extend it, it will cut somewhere at -5. So this was the waveform. Okay, so this question was asked in GATE 2010. So go back and look into the question, see the options, and check where you will be getting the output and where you will not be getting the output. If you so this is an analytical question, and this is a very good question. Okay, this is a kind of a rectifier question, right? So please go back and analyze this question. GATE 2010 EC. Okay, and you will find similar problems. I think there are similar problems in Cedra and Smith, and as far as I remember, this was taken from this book. Okay, the similar questions are have come in IES also. I'm not sure, but I think I have seen this kind of problems in Cedra and Smith. Okay, so just go back and check this. So I hope whatever I have done is clear. Once you figured out the diode on and off, the question is solved. Let me know once you are done with it. Okay, so just look into it once. One more information that I had to give. So 2 weeks before I was going with the small signal analysis of MOSFETs, and we got stuck at a point where in the derivation. So I was doing something wrong in the derivation. There was a silly mistake. That's why I could not come up with a solution. I had uploaded it that day itself in YouTube, but I forgot to mention it in the class. So I think it was last to last class maybe. Last class we did MOSFETs, before that we did Opamps. So before that, the class before that. So 2 classes before. Uh, pretty, yeah, it has been many days. So I had made the change, and you can go and see that in the thing, the small signal analysis of MOSFET, the derivation that we were doing. Okay. Right, Sarah. The diode actually makes it half cycle. So if the diode is not present, okay, so let me see which question to take next. This one is a good question. This one is a simple question. Actually, the other one is. Okay. So let me know if we can go to the next question, or should I go back? So the earlier one that you had seen, it was actually a precision rectifier. So with the op-amp, when a diode is used, it is called a precision rectifier. You would have heard it. Okay, so let's start with the next question now. Okay, get 2080. Now you can see that the op-amps are not alone. There are these diodes with the op-amp or a transistor with the op-amp. So you should be prepared with this kind of questions. Okay, this kind of questions can come. So op-amp is ideal. Zener diode voltage is 2.5 volts and a unit step is applied. Okay, so what will happen to a Zener diode? Zener diode at breakdown, it just shows it behaves as a voltage source, right? So assuming that it is in breakdown right now, how it comes? It comes like this, right? Plus minus 2.5. Okay, so that means the capacitor voltage is plus minus 2.5 volts. Okay, and the output, and why this happened? Because the output crossed 10 volts, right? Output crossed 10 volts. So output crossed 10 volts, that means Zener diode is at breakdown. It is now on with a voltage of plus minus 2.5 across it, and the same plus minus 2.5 is across 1 microfarad. Clear? Okay, so now this is 0 volts, and since this is 1 volt, after t equals to 0, this has become 1 volt. So, okay, I should have actually read out the question first to you. So, op-amp is ideal, Zener voltage is given, V in is given, and they are saying at t equals to 0, voltage across both the capacitors is 0 volt. That is, they are initially uncharged. And V out crosses minus 10 volt, and what is the time when V out crosses minus 10 volts? So I'm considering V out is crossing minus 10 volts, so that is V out is minus 10 volts, Zener is at breakdown, right? And 1 volt is at input. It is a matter after t equals to 0, so 1 volt is at input. So what is the current from here? It is 1 milliampere, right? 1 minus 0 by 1 kilo, 1 milliampere. Now nothing goes inside the op-amp. So this 1 milliampere travels from here, 1 milliampere, right? Basically coming from here, like this, 1 milliampere. So that is the current across this is 1 milliampere. Right? So here I have drawn it. You can see V out is minus 10 volt, I is 1 milliampere, and voltage across the capacitor is what? 1 by C integration of I dt. Right? And since Iz is not mentioned, I am not taking it. Okay? And therefore, what will happen? So, since this is minus 10 volts, this is plus minus 2.5. Right? This is plus minus 2.5. So, what is the voltage across this capacitor? 7.5. Right? So, plus 10 minus 10 is 0 volts. So, KVL completes. Correct? And the current is 1 milliampere. Correct? What they had asked? They have asked the time. So, VC is equals to, you know, right? Simple, put 7.5 equals to 1 milliamps by C is 1 microfarad into T. Just put in the values, see what T you are getting. That will be the answer. 7.5 milliseconds. Okay. So I hope this question is clear. We first found the current through this capacitor. Okay. And then they have asked time when V out will be minus 10 volts. We have taken minus 10 at V. So the time where V out is at minus 10 volts, the capacitor voltages are like this, right? So 2.5 is what across Zener diode. So obviously the other capacitor will be having 7.5 volts. Okay, and since IZ is not mentioned because I don't know the current here, I cannot use this capacitor, right? Therefore I am using the other capacitor where I know the current, I know the voltage across it, and therefore I can know the current, know the time it takes to charge that capacitor to 7.5 volts, and that will be the same time which will be taken by node V out to got charged to minus 10 volts, right? Because when V out is at minus 10 volts, then only the other capacitor is at 7.5. That is the same time. So 7.5 milliseconds. Okay, just look into the question. Let me know once you are done with this. Okay, so there is 5 minutes left. I don't think I'll be able to finish another transient question, so I'll take that up next week. And let me know any topic that you would like to take next week, because I have taken Opamps 2 classes. MOSFETs last week I had solved all MOSFET problems. So what else do you want me to solve in analog? Or any question you want to kind of any topic you want kind of revision or something, that will also be fine. BJT region of operation. Okay, so you want it with graphs and all that, you want explanation, because they won't be asking direct, I think. You So DC analysis is what defines the region of operation, so that with questions. Okay, okay, I think region of operation direct questions are few, but amplifiers is what they ask more. That is when the BJT is already in active region of operation. So I'll try to find out some problems. Okay, then Chandrasekhar, can you do one thing? By Wednesday, can you send me questions? Okay, because when I search questions, I just think I just want to take the difficult ones and solve it. But you might already have those questions which you find difficult, so that will be easier for me. So by Wednesday, please send me the questions. I'm telling this to everybody. Swati, Sara, Racha, Jayesh, Shreya, whatever questions you guys want. By Wednesday, you send me. By Wednesday, whatever questions you guys send me from GATE previous year, I'll be solving that in Saturday class. Okay, so next Saturday, I'm not going to take out any questions apart from whatever you have sent me. Okay. Okay, and I have already uploaded the this live video sessions in YouTube. If you have any doubt, you can always go back and check them out. Okay, and I think the NPTEL team will also be providing the links sometime soon, or I don't know if they have already provided it. Okay, so if there are no more questions, then I will wind up the session. Okay, thank you everybody. Okay, bye.